Today, what I wanted to talk about is, in particular, kind of what I was referring to earlier as the how exercise. The how exercise is after you've specified what you're going to do. How is when you figure out how you're going to do it. This is design, and this is what all engineers wait for. You'll notice that I kind of had to force you away from designing things or focusing too soon. You finally get to do that. You finally get to figure out how to solve the problem, not just specify it or not just talk about it in this way. One of the reasons why we take so long to get to this stage is because you want to be as thorough as you can in the early stages when making changes is cheap. Changing a specification is very inexpensive. We're talking dollars. Changing a design, tens of dollars to hundreds of dollars. Changing after prototype, we're getting into the thousands, and changing after it get into the field, we can run up into the millions. And so we want to be as thorough as we can. So I've titled this Design the Pinnacle of Engineering. Really it is. When you think about design and engineering tasks and stuff, the fact of the matter is without a designer, nothing would exist. No one would make anything, no one would invent anything. And so I really do see design as the pinnacle of engineering. So what I want to talk to today is just kind of a bit about the how exercise, and this is leading to your design review that will be your last assignment of the semester, and so that you can complete that. But I also want to teach you a couple technique, in particular called decision matrices, that allows you to do that. Okay, design is, in my opinion, why we engineer. And it's this interesting mix of things that don't sound like they go together. It's a methodical thing, it's an analytical thing, and it's a creative thing. And so I think that when you say design is methodical design is generally the difference between success and failure in engineering projects. The more methodical systems that you have, the better chance you have for success. It's analytical in that you get to use all that math and physics and engineering classes that you used in order to design. The approach is a little different. It's not analysis particularly, but it's synthesis, and you're using these analytical tools to allow you to synthesize something that does what you want it to do, which is the essence of design. And it's creative because you get to see things in different ways. You get to invent things that the world has never seen before. I often tell classes that if physicists ever really do come up with a theory of everything and they figure it all out, then there will be a lot of unemployed physicists. Engineers, however, will be taking physical law and manipulating it, physical and mathematical law, and manipulating it to produce new things forever. As an example of this, I was talking to Dr. Baker one day, and he said that for over 150 years, people have been writing down Maxwell's equations, manipulating them in some ways, and getting PhDs. And so it's exactly the same way in engineering. There's always something new to be invented or made. And so it's a very creative process. It's fundamentally creative, in my opinion. Okay, we started out, we have requirements. Now what do we do with them? Well, we have to design now to meet each requirement. And we really want to meet each requirement. We want to meet each requirement in some sort of optimal fashion. And we also want to demonstrate in our design and what we're doing that we're technically competent. Technical competence is we want to show that we have thought through this problem, that we haven't just come up with something or flailed something into existence till we get something that sort of works or works for long enough or something like that. We want to really demonstrate that we know what we're doing, and that's important. Meeting each requirement. So out of your specification, take any requirement that you have, and figure out 3 or 4 ways to meet it. So why 3 or 4 ways? Well, the reason that you want to do this is you want to show that you didn't just attach yourself to your first thought of how you're going to solve this problem. Pursue that until it is no longer pursuable, and then go back and start all over again. So 3 or 4 ways to meet. This is pretty standard. So if I've got a problem, I can say, how would I solve this problem? What's 1 way, 2 ways, 3 ways, 4 ways? And then you're going to figure out a set of selection criteria, and I give some examples that allow you to pick which of those solutions are best for that requirement. I've got a couple of examples. It can be cost, it can be ease of development, it can be ease of maintenance. All of those are possibilities. The criteria that you select, they're important, because if you get them wrong, or you don't weight things the correct way, then you'll pick something that isn't the best. But we'll talk about that in a little bit. But these are just some possibilities. There's a simple tool that's developed. It's called a decision matrix. And the decision matrix allows you to select the best option out of a set of options. And so the criteria by which you select, called the selection criteria, can be weighted. So I can make one criteria have a greater weight than any of the other criteria or something like that. And this really demonstrates technical competence, particularly when you're in a design review. As I said, you didn't run after your first idea. So first way you thought of solving the problem, you stopped and thought of other ways. And a lot of times what you will come up with is a better way, a better solution than your first thought. And then it also says you've considered what was important in the ultimate choice you're going to make. You came up with criteria for selecting what you were going to use, or how you were going to meet this requirement. And the criteria reflect your understanding of the problem. How well do you understand what this device is, or what it does, or the system you're trying to design? And now I decided to do an example, and this is just a decision matrix, and this is a low-pass filter example. And so I have a requirement in my system for a low-pass filter, this is to remove noise from a sensor signal, and I give it the following requirements. These are very technical requirements. They're not really critical to the problem or anything at this point, but I just kind of wanted you to see, how typical something would typically be specified like this. You've got an upper passband upper frequency, stop band lower frequency. You have passband attenuation. You have stop band attenuation, and so all of these give you the filter requirements. So if this were a filter used in my field of control systems, I'm going to make sure that the passband is much higher than the bandwidth of my system, so that this device doesn't interfere with its operation, and all that. And I've got a requirement for getting rid of noise at high frequencies that's greater than 60 dB down. And so from that, I can design the filter. But what I want to focus on is, instead of the filter specifics in this case, is I want to focus on technical approaches. All of these approaches that I described, I would be able to design a filter that took that signal and filtered it in some way that gave me what I needed. And so I picked 4 possible approaches. I picked an analog operational amplifier filter, easy to do, easy to build, all that stuff. Turns out in modern electronics they can be a little expensive, but we'll talk about that in a bit. I could do a digital approach using a field programmable gate array, FPGA. I could do a digital signal processor approach, or a DSP, and I could do a digital filter in a microcontroller. So all of those are possibilities for the filter that I need to design to meet this requirement. So by not just saying, oh, I'm going to do it with a DSP, or oh, I'm going to do it with an op-amp, I can then look at the possible things that are critical and help me select the best choice for my specific system. Okay, I picked some selection criteria. I selected a manufacturing cost, a maintenance cost, field modifiability, lifetime stability, in other words, does it remain the same filter for its life, and whole system compatibility. Obviously, the weights, as you see, I've got manufacturing cost and whole system compatibility are both weighted 1, whereas field modifiability, I give that a 0.5. It's not as critical as some of the others. And I've got maintenance cost at a 0.8 and lifetime stability at a 0.9. And so those are things that are important to me in designing this filter. This is when I'm sending it out into the field, these are the things that I want. I obviously I want it to be compatible with the rest of the system. So if I've looked at other requirements and I'm slowly coming to the conclusion that maybe a microcontroller might be the way to go for this system, then I would want my filter to be compatible with the use of that microcontroller. Could I put it in the microcontroller that I'm going to use for the rest of the system? Those are kind of questions that I have to ask at this point. And then I've got a low-pass filter example, the selection matrix here. You'll see what I've got over here are all the technical approaches. Up here are the selection criteria that I just wrote down there. Lower numbers are worse, and I give everything a 1 to 5 ranking. So I go through operational amplifier, manufacturing costs. The reason this is so expensive is not due to semiconductors, is remarkably due to things like capacitors. They're going to add quite a bit of expense to this, and so I rank that at a 2. FPGAs, they tend to be expensive. You tend to have to do a fair amount of custom work. DSPs also more expensive than typical microcontrollers. They're different. Their software is a little different. And then I've got the so I gave those all 2s. I've got the microcontroller rated at a 4. Maintenance cost, operational amplifier, there is essentially none. When I'm talking about maintenance, in this case, it would be software maintenance. How do I, once I build it, I don't have to maintain it. It does what it needs to do. So that's ranked highly in this case. FPGA is ranked low just due to the FPGA software, the VHDL or Verilog code that I have to maintain, all those kind of things can be expensive. Software isn't the end all and be all because of maintenance. I have to maintain a code base. I have to update a code base. I have to do all those kind of things. And I give the DSP the same thing. And microcontroller, I rank it as 4 because they're so common and available that that I could likely find one and maintain it for cheap. I do still have a software base to maintain, however. Field modifiability, operational amplifier, very difficult to modify in the field. I would physically have to unsolder and resolder components. FPGA, I give it a 3. A little more difficult to just modify on the fly. And DSP and microcontroller, I give 4s for both of those. And we'll talk a little bit about what you may recognize at this point as some of this is pretty arbitrary, but it's important to go through the exercise because it makes you think about what's required and what might happen. Lifetime stability, capacitors change with time, and so my filter will change over time. So I gave it a 1. All of these 3 are digital, and so they're going to be the same thing. Whether the thing is good or bad is not the issue. It's going to be the same thing. And then whole system compatibility. Operational amplifier, I would have to add an entire analog section to my system, which I may or may not want to do. I may or may not. It may be expensive. FPGA is typically, if I'm going to put an FPGA, it's going to be a specialty project. And so I may not, unless I'm doing the rest of the system in an FPGA, then I'm not going to want to include that, or that's not going to give me whole system compatibility. DSP, same thing. DSPs are kind of specialty things, whereas a general purpose microprocessor may be able to fulfill all of the requirements I have, and so I gave that a 5. I look over here at weighted sum, and you can kind of see the different pieces. I've got an 8.4 for operational amplifier is the lowest, but then down here the microcontroller is a 17.2. And so you'll notice that these three kind of grouped, they're very close to each other, while this one stood out. And that's kind of what we're looking for when we do an FPGA. The weights, by the way, are down here. These are just what I use to give those numbers. Okay, so this selection or this selection matrix allows me to find out what would be best for the system I have. Now, there's a couple of comments I have. Obviously, the selection matrix process, decision matrix, I called it a selection matrix. Just a second. Okay. I wondered why I was having that sensation while I was saying that. Decision matrices, they're just as good as only as good as the design alternative you've selected, the criterion that you've selected, and the weights you've given to those various criteria. Now, as I say, the process is not perfect, but it is better than just cause. In other words, if you just say, well, I just did this because I could, or it just popped into my head and I did that without thinking of alternatives. And the other thing is you will get better at it with practice. You will become skilled at doing this, and you can create these matrices, and they really will help you make better designs and better systems designs. Okay, just some parting comments for this commentary. For your project design review, what you're going to do is select 3 or 4 of your critical systems requirements. Okay, and then I want you to use decision matrix to develop possible solutions and devise selection criteria and weights, and select the best option based on your requirement, on your criteria and weights for each of those requirements, each of those 3 or 4 requirements. And then you're going to save your decision matrices. You can put them on your homepage, and you're going to include these in your design review slides. Part of a design review is proving to the audiences listening to you talk about your design that you are technically competent. And nothing proves competence than broad systems thinking in a design review. And so in general, people will sit up and take notice when you do that. Okay, that's the end of this one. Thanks for listening and tolerating this strange time. Anyway, we will see you again.